Hi everyone. In this video we're going to do a quick surface exercise, and this will be kind of a preliminary introduction to parametric fields, or how we can actually build a parametric field condition in Grasshopper. So for this exercise I'm actually going to use a hexagonal grid. But before we begin, I want to actually show some of these principles in a 2D environment, and where we can actually maybe understand the parametric logic of this field condition a bit better. So I'm actually going to create a point grid to begin with. So there are multiple ways we can create point grids. We can go to vector, there's grid here. We can start with a square or rectangular grid, or you can build it bottom up using the series and the points function. So in the series I'm going to specify an interval of 2, and let's say we want 20 in one series and 20 values, and for the other one let's say we want 30, or let's make it 35. So I want this to represent kind of the resolution in the x direction, this to represent resolution in the y direction, so these will be the proportions. So I'm going to do a cross-reference, interlink these two, and then construct point. So this will be x, this will be y. We did it the other way around actually. Let's change this to be, this was supposed to be x actually, and this is supposed to be y. So let's make this 20, and this is going to be 35. Now that we have the point grid, I actually want to place a geometry here that we can manipulate using a parametric condition. So by default this could be a simple circle. I'm going to place a circle at each point, and when we specify the radius to be 1, you can see that they're actually going to be tangential to each other. So I'm going to hide the point grid here. Now what I want to do is create a condition where we can actually control the behavior of these circles. So for instance, what if they didn't all take a radius as 1, but what if we actually control their radii according to some distance to a point? And in this case the point could be an attractor that controls this field. So in order to do this, we have to create an actual point geometry that we can move around. So this would be that point I'm going to use, and we need to link it to Grasshopper using this point container. You can also find it under parameters, geometry point, and I'm going to right click here and do set one point and choose the point. Now the way we're going to calculate the distance is through these points. So remember, we are placing circles at these points. So if I type in distance, these will be the distances of all these grid points to that point attractor. We can also visualize the distance as lines so that we can see how changing the point actually affects the field condition. Now these lines actually represent the distance of this point to each grid point, and we can see that some of them are longer and some of them are shorter. So this will actually inform us on how to constrain this field. I'm going to temporarily turn off the lines so that we are not confused. But what I want to do is actually a few things. For instance, we can use the distance and basically have this as a driver for how the radius values are going to be. For instance, if I quickly feed this in to the radius values, you can see that the values are so large that the circles actually do intersect with each other. One way to control this is to divide the distances with some values. So let's say we do divide them by 50 and feed them in to the radii. Now we're getting a bit of better behavior. So now you can see that depending on what this threshold is, we can actually control the behavior of the fields. So I'm simply dividing the distance of these grid points to this point and to derive the radii. But this is actually kind of the beginning point of where we want to be. For instance, you can see that no matter what this threshold is, some values still create larger values than 1. What if we want to actually limit this to some threshold? And we can actually do this by using a few different options. So rather than dividing it, we can actually use a function called remap, which takes in a value within a specific domain and maps it into another domain. So in this case, we have a few inputs. The value to remap would be the distances. The source domain would be the domain of this distance. For instance, what is the maximum value and what is the smallest value in this list? And we can actually easily retrieve it by using bounds. Bounds actually gives us the domain that is specific to a list of values. And this will give me the interval. So right now we can see that the closest value is 0.73 and the largest value is 49.5. And we want the target domain to be within something, right? But here we have an issue. For instance, we have in the target domain we have 0 to 1. So remember that initially we were supplying number 1 to the radius value. So 1 is going to be the largest value we want for these circles to be tangential to each other. But if I supply 0, then we get no geometry created there. So 0 radius is not something we want actually. So maybe we can actually do limit the output values to some threshold. For instance, I can simply construct a domain here and specify a value higher than 0, or I can filter the resulting values for zeros or that are below some threshold. For instance, if I were to look at bounds of the output here and attach a panel, you will see that the values go from 0 to 1. But if I were to filter, let's say, values below 0.1, how am I going to do that? So if you go to Math tab, and if you, let's see, I think it's under Utilities. If we do maximum here, what maximum does is it takes in 2 values and it always passes the larger value. So if I were to specify some threshold here, let's say our threshold is 0.2 or 0.1, then all the values below 0.1 will be replaced by 0.1. Now if I look at my bounds again, you can see that the lowest value now is replaced by 0.1. So if I feed this in to my radius, you can see that these values that might be below 0.1 are actually restricted to 0.1. So that's my lowest threshold. And if I move this point around, I will always see circles and they would always display some value. And we can also increase this threshold here. You can see I can actually make it limited to some other value. And if you want to increase the threshold of this, we can actually divide it with some value here, but I'm not going to go into that. This is basically the simplest parametric field condition that we can create with this exercise. Now, what I want to do is actually use this as a starting point and do a bit more development on top of this. For instance, by using this logic here, I'm going to build a different type of grid. Now let's go to the vector tab and grid tab. Here we have the hexagonal grid, and let's look at if we can do something similar in the hexagonal grid. So here we have base plane, size of hexagons, number of grid cells in the X direction, and number of grid cells in the Y direction. So let's specify some values here. So I'm going to do 20 by 40, and let's say this is my hexagonal grid. Right now I have an issue that these two grids are colliding. So what I can do is basically disable some input value for the top part of the code. So if I right click here and disable this, right now it's enabled, you can see that it's actually turned off. Now what that does is it doesn't supply any more values here, and everything, every circuitry that doesn't receive value is turned into orange, and our script doesn't actually execute anymore. Now we can actually focus on this part. Now our work isn't actually lost, it's there, it's just we just turned it off basically. So let's start with this. We have the hexagonal grid, we have the grid cell outlines, and we have points at grid centers. So let's look at where those points are. So if I were to extract them into the container, we also have some sort of a packed grid here, and I can build a similar relationship here, like the way we did in the top part. How do we do it? Well, we have the point attractor here. I can actually right click here and name this as Attractor, and I want to calculate the distance of these points to this attractor, so I can do distance. Now one thing I want to mention here is that the hexagonal grid outputs lists of values. So here, for instance, we have multiple data coming in, and that's actually represented by these dash lines. So dash line means this container outputs lists within lists. So if you want to create a single list here, we can right click and do flatten, and what that does is it will basically put all the data points into a single list, and that's actually how we want to calculate the distances. Now we got the distances, and the next thing is we can actually copy this portion out. So if I, let's say, want to use this logic that we built here, we can also use it in the hexagonal grid. So the distances will be the bounds, and they will be remapped again, and we're going to filter values that are below 0.1. And we're not going to place circles here this time. What we're going to do is actually I want to scale the hexagons down. So let's say we do scale, and the geometry that we want to scale are going to be the grid cell outlines. So let's create a curve output for those, and I want to right click and flatten that list as well, so that the data is matching here. So I'm creating two flattened lists, and I want to scale these geometries down. So how does scale work? We take in a geometry, center of scaling, and a scaling factor. So I want to scale the bounds, and I want to scale them at the centers, and I want to use these values as my thresholds. So if I were to let's see, hide these points, we can actually see the hexagonal grid taking shape. Now I have another issue here. We have set minimum value, let's say where the point is. We want the smallest hexagons scaled, but the largest value somehow kind of overlaps with the initial value, because we still have 1 as an output here. So remember, the furthest away value gets mapped as value 1, so that doesn't actually scale anything down. And we can fix this issue by using something else here. We can actually type in minimum, and now I can filter number 1 as 0.9, for instance. Just like we did here, values below 0.1 were filtered out. With minimum, I can actually filter values that are greater than 0.9, because if we get a value that is greater than 0.9, it will be replaced with this. So if I feed this in now, this value here will be fixed, and this will control the maximum aperture we want to have in our grid. So that's basically the shape that we want, and it's two-dimensional at the moment. Let's say that we want to render these as surfaces. How can we do that? Now we have the scaled versions here, and we have the original curves, and I need to couple these up. Let's say we want to loft them one with each other. So there are multiple ways we can do this. One of them is merge. So I can have multiple lists coming in here. But what merge does is it actually appends lists to each other. So this will output 1600 values. And if we try to loft this, it won't actually work. We have a lot of geometry. What we want to do is create each single cell as an individual. So just like we did flatten here, I want to do the reverse here. So I want to right click here and graft it. So what that will do is it will create a list for each of these items. And now they will be merged actually as couples, right? Because now they're actually fed in as lists. So when I graph this, 800 values become a list of lists, a list of basically each item will be placed in a list. And you can see that here. When you go over here, you can see that n equals 1 means there's actually one item in that list, whereas here we have 800 values. And if I do loft here, let's see what we get. Now all the surfaces have been connected. Now this is actually a good point to start, because now if we move that around, you can see that we get a different type of behavior. I'm actually going to take this one step further and make this in 3 dimensions. So I'm going to right click here, disable this for now, because it's also taking some time to calculate when we move this around. And after scaling it, let's actually try to move these up. So let's do something similar here. So what if we want to also give them some height? So just like we did the mapping for scale, we can actually do a mapping for height. So I can again use the same attractors, same distances, and remap those values to a custom domain. So we are not going to do minimum maximum this time, but we are going to specify some intervals. So I can do construct domain and specify the lowest height value and the maximum height value we want. For instance, let's say we want the smallest height to be 2, or actually let's make it a bit less than that. Let's actually make it 0.5, and the maximum value to be, let's say, 5. Now what that will do is these distances will get mapped to these values. So the closest cell point will get 0.5 as its height, and the farthest away point will get 5 as its height. Now these values, I want to use them to move the scaled hexagons in the vertical direction. So we can do that by using move function, and the move function takes in a base geometry and a translation vector. Consider this as how you do manipulation in Rhino. For instance, if you have an object and you want to move it, you can type in move, select the geometry, and you select from point to point, right? So whatever displacement I'm giving here is basically the translation vector itself. I can also do move, select the geometry, click a base point, type in 10, and move 10 units in X or Y direction or in Z direction. right? So essentially what we want to do is replicate this operation here, but the translation vector is going to be a z vector that is changed by these values here. So I can simply do that using z. Unit z is basically a vector. It's located under vector unit vectors. These are basically our unit directions x, y, and z. So you can directly supply in these values and it will give you the corresponding z vectors. And we can move these points according to the translation vector. So now you can see that wherever that point is, that's where the minimum height values have been created. And all I have to do to make these lofts work again is to connect the vertically displaced grid locations and enable the loft. So you can actually see now I have created hexagonal cells that are scaled and moved upward. It's a bit difficult to see it in this configuration, and we also have a point here. I also don't want to move that point, so I'm going to hide it temporarily. And let's bake it and see what that looks like. So there you have it. That's our parametric field with the cells actually lifted up and scaled according to their distance to this point. But what if we have not one point but multiple points, or what if we have a curve? Can we actually use those to also control this field? Yes, we can. So I'm going to quickly show that how that could be done. So let's imagine we have not a point but multiple points here. So I'm going to create another point container, and this point was hidden. I'm going to show it again, and let's create two more points. So these are the 3 points. So I want these 3 points to actually control this field now. So wherever those points are, I want the cells to be closed and not extruded too high. So before we do this though, this was actually run by a single attractor. Now that we have multiple attractors, the first thing I need to do is find which attractor is closest to which grid cell. And that is achieved by the closest point. So a closest point plugin basically takes in points to search from and cloud of points to search, and it actually gives you a point that is closest to the cloud of points. So my points to search from could be the cells, and my cloud of points could be the reference points. So let's see if we get the right distribution. I'm going to check it with lines. I'm going to connect the result with the closest points. Now you can see how this grid is being distributed between these values. So I'm going to just disable this portion here so that you can see. Now these cells, this cell is actually, we are actually calculating which point is closest. Apparently it's this point here, and if I move the configuration of these points around, so let's say we have now 3 cells actually dynamically updating here, and that will also change how these cells are distributed. Now that these are my target points, I can use them for my distance, and that's all I have to actually add. I'm just going to replace this attractor with whatever I get with the closest point. And if I enable this, we should get a more dynamic field where the 3 cells are now controlling how much closure we have at their location. And I'm going to bake this as well so that we can compare it to the previous example. And there you have it. So now we don't have a single closure, we have actually 3 closed areas because we had 3 points. This could be as many points as you want. You can also change these thresholds here to control the behavior. And you can also try other types of grids. For instance, I tried hexagonal grid. You can also try rectangular grids, triangular grid, or square grids, and see what kind of shapes you can come up with.